Betelgeuse. For centuries, this red giant has burned in the shoulder of Orion, glowing like a cosmic ember visible even to the naked eye. Ancient civilizations watched it. Sailors navigated by it. Modern astronomers studied it with fascination and caution. And then, without warning, its brightness spiked by nearly 250%. When data from the James Webb Space Telescope confirmed the increase, observatories around the world went silent for a moment. Because Betelgeuse is not just any star. It is unstable, massive, near the end of its life. And when a star like that changes suddenly, the universe is telling us something. The James Webb Space Telescope, positioned far beyond Earth at a gravitational balance point nearly 1,000,000 miles away, does not simply take pictures. It reads heat. It detects faint infrared signatures invisible to human eyes. It peers through dust that blinds other telescopes. So when Webb recorded this surge, it wasn't atmospheric interference. It wasn't optical illusion. It was real. But what does a 250% increase in brightness actually mean? To understand that, we have to understand Betelgeuse itself. Located about 640 light-years away in the constellation Orion, Betelgeuse is a red supergiant. If placed at the center of our solar system, its outer surface would stretch past the orbit of Mars. Possibly even Jupiter. It is that large, that swollen, that unstable. Red supergiants are stars in their final chapter. They have exhausted the hydrogen fuel that once powered their stable youth. Now they burn heavier elements in chaotic layers, like a furnace running too hot for its own structure. Inside Betelgeuse, nuclear reactions rage in stacked shells. Helium, carbon, oxygen. Each layer fusing under crushing pressure. Each stage shorter than the last. It is a countdown written in fire. In 2019 and 2020, Betelgeuse dimmed dramatically in what scientists called the Great Dimming. For months, its brightness dropped in a way that sparked headlines around the world. Was it about to explode? It didn't. Instead, astronomers later discovered that a massive cloud of dust had been expelled from the star, temporarily blocking its light. But this time is different. This isn't dimming. This is intensifying. The James Webb Space Telescope detected not just visible brightening, but changes in infrared output, suggesting activity deep within the star's outer layers. That kind of signal cannot be dismissed as surface dust alone. Is Betelgeuse shedding mass again? Is it experiencing violent convection on a scale we barely understand? Or is this the prelude to something far more dramatic? When massive stars approach the end, they do not go quietly. Their outer layers pulse. They swell and contract. They eject material into space. Their cores compress under gravity's relentless pull. And somewhere in that chaos lies the threshold, the moment when the core can no longer resist collapse. When that happens, the result is a supernova. If Betelgeuse were to explode, it would briefly shine brighter than the full moon in Earth's sky. It would be visible during the day. For weeks, perhaps months. But let's pause. A brightness increase does not equal imminent explosion. Stellar death is complex. Timescales are tricky. Soon, in astronomical language, can mean tomorrow, or 100,000 years from now. And yet, a 250% surge forces scientists to look again. To measure more carefully. To ask sharper questions. Why now? What changed inside that colossal furnace? The James Webb Space Telescope was built to answer questions like this. Not just to observe distant galaxies at the edge of time, but to dissect the physics of stars in exquisite detail. Webb sees the heat patterns on Betelgeuse's surface. It tracks the movement of gas. It detects chemical fingerprints in the expelled material. It gives us data no telescope before it could capture, including the Hubble Space Telescope, which, though revolutionary, cannot see infrared with Webb's clarity or depth. This moment, this sudden surge, reminds us that the sky is not static. Stars live. Stars change. Stars die. And sometimes, they flare with a warning. But here is the deeper question. If Betelgeuse is entering a new, unstable phase, what else might Webb uncover about the life cycles of massive stars? About the forces that sculpt galaxies? About the elements that eventually become planets and life? Because every atom in your body was forged in a star. And somewhere, 640 light-years away, a giant red sun just grew brighter. Is it a final breath? Or simply another convulsion in a very long death? Long before Betelgeuse brightened, before its surge rippled through observatories on Earth, there was a different kind of ignition. Not in a star. In human ambition. The James Webb Space Telescope did not begin as metal and mirrors. It began as a question: how far back can we see? For decades, the Hubble Space Telescope transformed our understanding of the cosmos. Launched in 1990 by NASA, it revealed galaxies colliding, nebulae blooming, and deep fields packed with thousands of distant galaxies in what once appeared to be empty space. Hubble showed us that the universe was more crowded, more violent, and more beautiful than we imagined. But Hubble had limits. It sees primarily in visible and ultraviolet light. And as the universe expands, light from the earliest galaxies stretches, redshifts, into infrared wavelengths. The older the light, the redder it becomes. Eventually, it slips entirely beyond Hubble's reach. If we wanted to see the first stars ignite, we needed new eyes. That is why NASA partnered with the European Space Agency and the Canadian Space Agency to build something unprecedented. A telescope not just larger than Hubble, but colder. More sensitive. Tuned specifically to infrared light. The James Webb Space Telescope launched in December 2021. Unlike Hubble, it does not orbit Earth. It traveled nearly 1 million miles away to a gravitational sweet spot known as L2, a place where the Sun, Earth, and telescope align in a delicate cosmic balance. There, shielded by a 5-layer sunshield the size of a tennis court, Webb cools itself to temperatures below -370 degrees Fahrenheit. Because to detect faint infrared light from the early universe, the telescope must be colder than the objects it observes. It carries a segmented gold mirror 6.5 meters across, more than twice Hubble's diameter. Each hexagonal segment unfolds in space like petals of a mechanical flower. Together, they collect more light than any space telescope before it. More light means deeper vision. And that vision has already rewritten cosmic history. Within months of beginning operations, Webb released its first deep field image. A patch of sky no larger than a grain of sand held at arm's length suddenly revealed thousands of galaxies, some so distant that their light began traveling toward us just a few 100 million years after the Big Bang. We were looking back over 13 billion years. Webb has identified galaxies forming far earlier than models predicted. It has detected surprisingly mature structures in what should have been a chaotic infant universe. Massive galaxies appearing too soon. Stars igniting faster than theory allowed. Each discovery forces astrophysicists to rethink timelines. But Webb's power is not limited to ancient galaxies. It peers into stellar nurseries where new stars are born inside thick veils of dust. It analyzes the atmospheres of exoplanets, detecting water vapor, carbon dioxide, even methane, molecules linked to the chemistry of life. It has captured detailed images of the pillars of creation, first made famous by Hubble, but now seen in infrared clarity that reveals stars forming within those towering columns of gas. And now, it has turned its gaze to Betelgeuse. What makes Webb uniquely suited to studying a red supergiant is its ability to see heat signatures and penetrate dust clouds expelled from the star's surface. Where visible light telescopes might see only brightness changes, Webb sees structure, motion, temperature variations across the star's bloated surface. When Betelgeuse surged by 250%, Webb did not just record a number. It recorded a story unfolding in infrared wavelengths. Surface convection cells the size of entire solar systems. Gas plumes erupting outward. Layers expanding and contracting. Hubble could observe some of this. Ground-based telescopes could track brightness shifts. But only Webb can combine sensitivity, resolution, and infrared depth in one instrument. And here's the quiet truth. Webb was built to look at the beginning of the universe. Yet one of its most compelling stories may unfold much closer to home. Because Betelgeuse is not ancient in cosmic terms. It is a relatively nearby neighbor in our galaxy. Watching it change in real time reminds us that astronomy is not only about the distant past. It is about dynamic present. Stars are not frozen points of light. They are evolving systems governed by physics we are still trying to fully understand. Webb bridges two extremes, The first galaxies ever formed and the dying giants in our own galactic backyard. From the birth of light to the brink of stellar death. And in between, a deeper question emerges. If this telescope can reveal the infancy of the cosmos and dissect the instability of massive stars, what will it show us next? How many assumptions about space are about to shift? Because every time we build better eyes, the universe surprises us. And Betelgeuse may just be the beginning. Imagine standing beneath a night sky where one star suddenly rivals the moon. Not for a moment. Not like a shooting star that vanishes in a blink. But a steady, blazing beacon where Orion's shoulder once glowed red. That is the promise, and the uncertainty, surrounding Betelgeuse. A 250% increase in brightness does not mean explosion is imminent. But it does mean instability. And instability, in a red supergiant, is never trivial. To understand why, we need to step inside the heart of a massive star. Betelgeuse was born millions of years ago from a collapsing cloud of gas and dust. It began life far more massive than our Sun, likely 15 to 20 times heavier. Massive stars live fast and die young. They burn through their nuclear fuel at astonishing rates. Our Sun will shine for roughly 10 billion years. Betelgeuse will not. At its core, nuclear fusion once converted hydrogen into helium, releasing the energy that pushes outward against gravity's inward pull. That balance, fusion versus gravity, is what keeps a star stable. But massive stars evolve quickly. Once hydrogen is depleted in the core, the star contracts. Temperatures rise. Helium begins to fuse into carbon and oxygen. Then carbon into neon. Neon into oxygen. Oxygen into silicon. Each stage burns hotter and faster than the last. Near the end, silicon fuses into iron. And iron is the end of the line. Fusing iron does not release energy. It consumes it. When a massive star builds an iron core, fusion can no longer support the crushing weight above it. Gravity wins. The core collapses in a fraction of a second. Then comes the rebound. A shock wave rips outward. The outer layers are blasted into space in one of the most violent events in the universe, a supernova. In that explosion, elements heavier than iron are forged. Gold, uranium, nickel, the building blocks of rocky planets and, eventually, life. Betelgeuse is somewhere in this late evolutionary sequence. We know it has left the stable hydrogen-burning phase long ago. We know it is bloated and unstable. We know it is shedding mass. But pinpointing exactly where it stands in the countdown is extraordinarily difficult. This is where the James Webb Space Telescope becomes crucial. Webb's infrared instruments can analyze the chemical signatures in the material Betelgeuse ejects. By studying isotopes and surface composition, astronomers can infer what fusion processes are occurring deep inside. The recent brightness surge suggests enhanced convection, giant bubbles of plasma rising and falling across the star's surface. These cells are so large they dwarf our entire solar system. Think about that. Storm systems larger than the orbit of Jupiter. When those convective motions intensify, they can push vast amounts of material outward. That material cools into dust. Dust clouds can both dim and brighten the star depending on their distribution and temperature. During the Great Dimming of 2019, a dust cloud temporarily obscured part of the star's surface. Webb's new data indicates something more energetic, possibly a large-scale restructuring of its outer layers. Is the core contracting further? Is a new fusion stage beginning? Or are we witnessing a star struggling to maintain equilibrium for just a little longer? Astronomers are careful. They avoid dramatic predictions. Because in cosmic time, near death might still mean tens of thousands of years. But here's what makes Betelgeuse different. We can observe it in extraordinary detail. It is close enough to resolve surface features. Close enough for Webb and other observatories to monitor changes over months, not centuries. We are watching stellar evolution unfold almost in real time. And if, someday, Betelgeuse does explode, it will not threaten Earth. At 640 light-years away, we are safely distant. The radiation would not harm us. Instead, it would be a spectacle. A cosmic fireworks display that reshapes Orion's familiar outline forever. For ancient cultures, such an event would have seemed like an omen. For us, it would be data. Incredible, transformative data. Webb would capture the infrared glow of expanding debris. Spectrographs would dissect the explosion's chemistry. We would witness heavy elements forming before our instruments. A laboratory experiment on a galactic scale. But even if the explosion is not imminent, the brightness surge is teaching us something critical. Massive stars are more dynamic than our models predicted. Their outer layers are chaotic. Their mass loss may be episodic and violent. Their pre-supernova behavior could include warning signs we are only beginning to recognize. What if brightness fluctuations are part of a pattern? What if Betelgeuse is rehearsing for its final act? And if we can decode that pattern here, could we identify similar signals in distant galaxies? Because somewhere, right now, countless massive stars are nearing collapse. Too far away for us to resolve clearly. Betelgeuse is our nearby test case. A living, burning experiment. And as Webb continues to watch, one question lingers like the red glow of Orion in winter skies. Are we witnessing the slow tightening of gravity's grip? Or simply another pulse in a giant star's restless heart? The universe does not send notifications. No alarms. No countdown clocks. Just light. When Betelgeuse brightened by 250%, it wasn't simply a spectacle. It was information traveling across 640 years of space to reach us at this precise moment in history, an era when humanity finally has the tools to understand it. And that may be the most extraordinary part of this story. For most of human existence, stars were symbols, guides, myths, fixed points in a celestial dome. Orion hunted eternally. Betelgeuse glowed red and steady. Now we know better. The sky is alive. The James Webb Space Telescope represents a turning point in that awareness. Built by NASA in partnership with the European Space Agency and the Canadian Space Agency, it is more than a successor to the Hubble Space Telescope. It is a new kind of perception. Hubble showed us that the universe is expanding and that galaxies fill even the darkest patches of sky. Its deep field images changed textbooks and humbled assumptions. But Webb goes further, literally and figuratively. It sees the first galaxies forming after the Big Bang. It detects starlight stretched across billions of years. It analyzes the atmospheres of exoplanets orbiting distant suns, searching for chemical fingerprints that might hint at habitability. And now, it studies the life cycle of a massive star in our own galactic neighborhood. Why does that matter? Because everything is connected. The iron in your blood, the calcium in your bones, the oxygen you breathe. These elements were forged inside ancient stars that lived and died long before our sun existed. Supernovae seeded space with heavy elements, enriching future generations of stars and planets. Without stellar death, there is no planetary chemistry. Without planetary chemistry, there is no life. Betelgeuse's instability is not just about one star nearing its end. It is about understanding the process that makes complex matter possible. Webb's observations of brightness surges and mass ejections refine our models of how massive stars lose material before exploding. That affects how we calculate supernova energy, how we map element formation, how we interpret distant explosions observed across the universe. If we can decode the behavior of Betelgeuse, we gain a template, a framework for recognizing similar pre-supernova signals in faraway galaxies. Imagine identifying a star on the brink of explosion years before it happens. Imagine coordinating telescopes across Earth and space to witness the event from its first flash. We are approaching that level of predictive astronomy. And this is only the beginning. Webb has already rewritten our understanding of the early universe, revealing galaxies forming earlier and faster than expected. It has shown that cosmic history may be more complex than our models suggested. It has detected carbon dioxide and water vapor in exoplanet atmospheres, moving us closer to identifying worlds that could, one day, host life. Each discovery shifts perspective. But perhaps the most profound shift is psychological. For the first time, humanity possesses instruments capable of watching stellar evolution unfold in detail. We are no longer passive observers under a static sky. We are investigators of cosmic processes. We ask sharper questions now. How do stars really die? How do galaxies assemble? Are we alone? Betelgeuse's surge is a reminder that the universe is dynamic on timescales we can witness. It collapses the illusion that cosmic change only happens over millions of years beyond human relevance. Something changed in that star. And we saw it. As Webb continues scanning the heavens, more surprises will follow. Unexpected galaxies. Strange exoplanet chemistries. Stellar behavior that defies prediction. Every time we think we understand the universe, it expands, conceptually and physically, beyond our grasp. But here is the quiet truth beneath all of it. We are made of star remnants studying the stars that made us. Betelgeuse will eventually explode. Maybe tomorrow in cosmic terms. Maybe long after our civilization has transformed beyond recognition. When it does, the elements forged in its core will drift into space, joining the raw material for future solar systems. Perhaps somewhere, billions of years from now, life will form around a star enriched by Betelgeuse's ashes. And if that life looks up at its sky, it may wonder about its origins. Just as we do. The 250% surge is not the end of a story. It is a chapter in an ongoing dialogue between humanity and the cosmos. A reminder that the universe is not distant and detached. It is active, evolving, and willing to reveal its secrets, if we build the courage and the tools to look.